Today we're going to go through sections 20.8 to 20.11. So we're going to talk about oxidation of aldehydes briefly, and we're going to talk about also organometallic reagents and how they react with things. So if we think about aldehydes, they look like this. Aldehydes can be oxidized to carboxylic acids. So ketones can't be oxidized anymore, but aldehydes can. It can be oxidized to carboxylic acids. There's a whole bunch of reagents that work. You've seen a lot of them before. So options are like chromium oxide or sodium dichromate or potassium dichromate or potassium permanganate. These are a whole bunch of options that would work. You can also selectively oxidize aldehydes, so it would only oxidize aldehydes and not other kinds of alcohols, etc. So for selective oxidation of aldehydes, you would use silver 1 oxide, so Ag2O, in aqueous ammonium hydroxide. And that's called the Tollens reagent, and it precipitates out silver metal, so it reduces the silver metal as your aldehyde gets oxidized. So let's talk about organometallic reagents. An organometallic reagent has some sort of carbon-metal bond. And because those metals are less electronegative than your carbon looks like this, and your metal looks like this. So your carbon is going to react like a carbanion when it reacts with things. Usually this metal is lithium, magnesium, or copper. So it makes that carbon have a partial negative charge because the metals are less electronegative than carbon. So examples would be like our lithium, so that's an organolithium reagent. If you have magnesium and then some sort of halogen, these are called organomagnesium reagents. They also have another name. They're also called Grignard reagents. And then the copper reagents have two R groups stuck on the copper, and only one of those R groups reacts. But those are our organocopper reagents, or called organocuprates sometimes. So the more polar the carbon-metal bond is, the more reactive it is. And so the organolithium and organomagnesium reagents are very reactive. And the organocuprates are more mild. So only one R group reacts, and these guys are more mild. So overall, it's going to act like a carbanion. It can either act like a base or like a nucleophile. So it can abstract protons or it can act like a nucleophile. So how do we make these organometallic reagents? You can buy some of the simple ones, but sometimes you want to make one with specific R groups on it. So if you want to make your organolithium or your Grignard reagent, you're going to just react an alkyl halide with the metal. So alkyl halide plus 2 lithiums gives you alkyl lithium reagent plus lithium halide. Or an alkyl halide plus magnesium, usually in ether or some sort of anhydrous solvent, is going to give you an R, and the magnesium is going to insert itself in between the R group and the halogen. If you want to make your organocuprate reagents, what you're going to do is take your organolithium reagent that you made above, and 2 of them, plus some sort of copper 1 salt. So we often use copper 1 iodide. Is going to attach 2 of those R groups to your copper, and that's going to be negatively charged, and your lithium is going to be positively charged associated with it, and then you're going to have lithium iodide left over. Acetylide anions are also examples of organometallic compounds. So if you take an acetylide anion, so something like this, and you add sodium amide, right, and you end up with this deprotonated with sodium attached to it. That's also an organometallic compound. It can do the same kind of thing. So how can these guys react as bases? They're super strong reagents and super strong bases, so they're easily going to take a proton from water or from an alcohol or carboxylic acid or an amine. So what happens is you have your organometallic reagent, and you have your alcohol or your water or things like that, and it's a base, so it's just simply going to take that proton off. Those electrons will go there, and you end up with a hydrocarbon and an alkoxide ion, or in the case of water, you would have a hydroxide ion. So we need to be aware of this, not because we want to make alkanes, but because these can be side products if you don't have your reaction completely dry without any water or any alcohol in it. Our organometallic reagents can also act as nucleophiles, so they can react with electrophilic carbon atoms to form new carbon-carbon bonds. So, few options for those. So, first option is the reaction of your organometallic reagent with aldehydes and ketones. So here's your organometallic reagent. You add your aldehyde or your ketone, and after you've added that organometallic reagent and it's reacted, then you quench it with water. So that provides your proton source, because we know that aldehydes and ketones do nucleophilic addition and not substitution. So the groups that were on there already stay on there, and you've added a new group from your organometallic reagent. So this is one way to make carbon-carbon bonds in reactions. Super helpful. Another option is reaction of these organometallic reagents with our carboxylic acid derivatives. And so that would be things like acid chlorides and esters, etc. So if you first add your organometallic reagent, you're going to end up with a ketone, or it's going to keep adding like it would to a ketone, and you end up with two of those R groups on there because you've done nucleophilic acyl substitution. So one thing it depends on is your leaving group, your Z. The other thing it depends on is your organometallic reagent. Which organometallic reagent? The other thing that organometallic reagents can do is they can react with like any other electrophilic functional group. So they can add to alkyl halides or epoxides or any of those things. Anything that a nucleophile could normally add to, these guys can add to as a nucleophile. So I want to give you just some basic mechanisms so you can see what's going on here. So our first mechanism is when they add to aldehydes or ketones. It's going to form an alcohol with a new carbon-carbon bond. So if you've got your aldehyde or your ketone and your organometallic reagent comes in, we're going to use a Grignard reagent for this one. Those electrons go up, open up the double bond. There you have your O minus, and now you can add your water in the second step, and those electrons will deprotonate the water. You end up with an alcohol. That's an H. and you've got a new carbon-carbon bond. So it adds one new R group. If your starting material is formaldehyde, so H is on both sides, you end up with a primary alcohol. If you have an aldehyde, it's going to make a secondary alcohol, and if you have a ketone, it's going to make a tertiary alcohol. So this works with all organolithium and Grignard reagents and acetylide anions. So organolithium, Grignard reagents, and with the acetylide anion. So, one thing you need to make sure of is that it's totally anhydrous conditions. You don't have any water around, because water will quench the organometallic reagent, so you only want to add it in the second step. You're going to end up with a racemic mixture of products because the achiral starting material and you have achiral reagents. So you get a racemic mixture. This is useful in lots of synthesis reactions. So how do we think backwards in our synthesis reactions? So if we think backward in synthesis reactions, you want to do first look at the carbon bonded to the alcohol. Secondly, you want to have one carbon group bonded to that carbon that came from the nucleophile. One carbon group came from the initial carbonyl. So one carbon group from the nucleophile and one from the initial carbonyl. So you want to break it into pieces and check the forward direction to make sure it works. Sometimes there's more than one possibility. So we'll look at some examples now. So if I want to use a Grignard reagent to make this compound, I look at the carbon bonded to the alcohol, this carbon right here. So we know that one carbon group bonded to that came from a nucleophile and one came from the initial carbonyl. And so if we make this our initial carbonyl and the one to the right to be our nucleophile, it would look like this. You can see those are our two possibilities. And either way I draw it, there's only one possibility for this particular problem. Let's talk about one where there's two possibilities. So here we also have a secondary alcohol, but you can see the two sides are different. So here's our carbon, that was our originally our carbonyl, and we can either have this side be the original carbonyl, or we can have this side be our original carbonyl. So the two possibilities look like this. There's one part, and the part that connects is always where you put your Grignard. So there's our other part. The other possibility would be So those are our two possible ways of doing this reaction. Either of them works. Thanks. See you next time.